For almost a century, we've had these two massive rule books for the universe. One describes gravity, and one describes cosmic expansion. And they don't really talk to each other. But what if they're not separate at all? What if they're both just different expressions of a single, deeper law? Today we're diving into a really radical idea called dynamic vacuum field theory, or DVFT, that suggests exactly that.
So the whole story really kicks off with this giant puzzle that's been nagging physicists for decades. There's a number called A0 that describes how stars move inside galaxies. And weirdly, it's almost identical to a completely different number that describes the expansion rate of the entire universe. Now, standard cosmology has always just shrugged and called this a free coincidence. But this theory asks a much more interesting question. What if it's not a coincidence at all? What if it's a massive clue to how the vacuum of space itself actually works?
So, how on earth does this theory pull that off? Well, here's our game plan. First, we'll break down exactly what DVFT is. Then, we'll see how it generates gravity from something called the phase of the vacuum. After that, and this is the exciting part, we'll uncover its one big falsifiable prediction. And finally, see how the James Webb Space Telescope is putting it to the ultimate test right now.
All right, first up, what exactly is dynamic vacuum field theory? At its heart, it's a complete rethink of where gravity comes from, and it's a huge departure from what we're used to with general relativity. Okay, this is the big conceptual jump. In Einstein's universe, gravity is all about geometry. Mass literally tells space-time how to curve, and that curvature tells mass how to move. But DVFT says, hold on, gravity isn't abstract geometry. It's a real physical force. It proposes that the vacuum isn't empty. Instead, it's a physical medium, kind of like a cosmic fluid with actual properties. Mass doesn't curve space, it physically deforms this vacuum medium, and it's that deformation that we experience as gravity.
So to actually model this, the theory describes the vacuum with this physical field. Now, you can think of it like the surface of a pond. It has an amplitude, which is kind of like the height of the waves, but the real key to gravity is something called its phase. That's the theta symbol. Imagine the phase is the exact position of a wave's crest. If that position changes really quickly from one point to the next, creating a steep gradient, that's where you get strong gravity. So here's the fundamental takeaway. In this picture, gravity isn't some fundamental force that's just baked into the fabric of space-time. No, it's an emergent effect. It's the vacuum itself physically reacting to the presence of mass, almost like water physically reacts when you drop a stone into it.
Okay, so we've got this idea of a vacuum phase. But how does it actually work out in the real world? Let's see how this single concept can explain both the crazy strong gravity near black holes and the subtle motions of entire galaxies.
This little equation right here, this is the engine room of the whole theory. It says that gravitational acceleration, that's g, is directly proportional to the gradient of the phase, that little upside-down triangle theta symbol. In plain English, the steeper the slope of the vacuum's phase, the stronger the gravity. It's just a beautifully direct and simple relationship.
And this leads to a totally new way of thinking about black holes. In DVFT, an event horizon isn't some abstract geometric point of no return. It's a physical surface where the vacuum medium itself gets so strained that its ability to send phase information outward just drops to zero. It's like a region of phase stagnation. Nothing can get out.
And right here is where the theory has to face its first huge test. When you actually calculate the radius where this phase stagnation kicks in, what do you get? You get a value that's identical to the famous Schwarzschild radius from general relativity. This is absolutely critical. It shows that DVFT, coming from a completely different direction, can correctly reproduce how gravity works in the most extreme places we know, passing a major sanity check.
Okay, so it works for black holes. Awesome. But let's go back to that bizarre coincidence. Why on earth would a number describing how galaxies spin have anything to do with the Hubble constant, which describes how the entire universe is expanding?
Well, DVFT's answer is that A0 isn't just some random number we found in galaxy data. It's a fundamental physical property of the vacuum itself. Think of it like the inherent tension in a stretched-out rubber sheet. A0 represents the vacuum's own natural tendency, its restoring acceleration, as it tries to snap back to a smooth equilibrium state.
So what sets the largest possible scale for this vacuum to relax over? Well, in an expanding universe, there's really only one candidate, the cosmic horizon, the very edge of our observable universe. And the size of that horizon is set directly by the Hubble expansion rate. This right here is the linchpin. This is what physically connects the properties of the vacuum on a local scale to the expansion of the entire cosmos.
And here's the payoff. When you run the numbers,
When you calculate what this vacuum acceleration should be based on the Hubble constant, including a geometric factor of 2 pi that just falls right out of the physics, you get 1.1 times 10 to the minus 10. The value we actually observe in galaxies? 1.2 times 10 to the minus 10. That is shockingly close. According to DVFT, it's not a coincidence. It's the same number because it's the same physics at work.
So now this whole thing gets elevated from just explaining a coincidence into something way more powerful, a concrete, testable scientific prediction. Let's see how this connection can actually be proven right or wrong.
This direct link to the Hubble parameter, h, leads to a truly stunning prediction. A0 can't be a constant. We know for a fact that the universe's expansion rate, h, was faster in the past. So if this theory is right, A0 must have been larger back in the early universe. This means gravity itself, on the scale of galaxies, behaved differently over cosmic time.
And that has a direct, observable consequence for how galaxies spin. There's a well-known rule called the baryonic Tully-Fisher relation that connects a galaxy's mass to its rotation speed. But VFT predicts this rule shouldn't be set in stone. Because A0 changed with cosmic time, this relationship should also evolve depending on a galaxy's redshift, on its age. All of a sudden, galaxies become these amazing time capsules, allowing us to probe the state of the vacuum throughout all of cosmic history.
Look, a theory is only as good as its predictions, and for the very first time in human history, we have an instrument that is powerful enough to carry out this specific, decisive test, the James Webb Space Telescope.
Now, to actually do this test, you need to measure 4 key things for really distant galaxies: how they're spinning, how much stuff is in them, how far away they are, and what the cosmic expansion rate was at that distance. For decades, getting all 4 of those for even a single ancient galaxy was just a complete pipe dream. JWST is the first telescope we've ever built that's powerful enough to nail all of them.
And the test itself is just beautifully straightforward. Here's how it works. You take a high redshift galaxy. Step 1, use its redshift to calculate what DVFT predicts A0 should have been at that point in cosmic history. Step 2, you use JWST's actual measurements of that galaxy's mass and velocity to figure out what A0 actually was. If the theory is right, those 2 numbers, they've got to match.
And get this, this isn't just a hypothetical future test. The very first test case on a distant galaxy from when the universe was super young has already been analyzed. Now, the measurements are still pretty new and have big error bars, but the initial result is consistent with the DVFT prediction. Under pretty reasonable assumptions about the galaxy's mass, the value of A0 they measured lines up almost perfectly with what the theory predicted it would be.
And this is what makes it real science. The theory puts its neck on the line. The criteria here are crystal clear. If the A0 we measure in distant galaxies changes in lockstep with the universe's expansion, the theory gets a huge checkmark. If A0 turns out to be constant through all of time, the theory is just plain wrong. It's a clean, decisive yes or no question.
And that's why this is so incredibly powerful. This isn't just about tweaking a dark matter model to fit the data. This is a direct test between 2 fundamentally different views of our universe. Are galaxies governed by local, invisible clumps of mysterious matter? Or are their dynamics a direct manifestation of a global property of the vacuum tied directly to cosmic expansion?
That test is happening as we speak, and it leaves us with this final massive question. For 50 years, our entire model of the cosmos has been built on the idea of dark matter. If the James Webb Space Telescope confirms that galaxy dynamics really do track the expansion of the universe, what does a cosmos governed by the laws of a dynamic vacuum actually look like?